Hello, and welcome to the TI Precision Lab series covering noise and ADC drive considerations for both SAR and Delta Sigma converters. In the last video, we looked in detail at digital filters and latency considerations. In this video, we will focus on how SAR and Delta Sigma converters are different from a noise perspective. We will also take a short look at input signal drive and voltage reference drive circuits for both topologies. This topic will cover both intrinsic and extrinsic noise sources for SAR and Delta Sigma converters. Intrinsic noise is naturally occurring and is generated by the circuit components themselves. Extrinsic noise is noise picked up from other circuits, and even the outside world. Intrinsic noise normally has a Gaussian distribution, but extrinsic noise does not have a Gaussian distribution. First, let's cover extrinsic noise. Some common types of extrinsic noise that can impact an ADC system are 50 or 60 Hz power line pickup, alias signals, RF noise, and power supply noise. Throughout this video, we will highlight any differences that may exist between SAR and Delta Sigma converters. Even for very low frequency systems, 50 and 60 Hz noise can be an issue. Some Delta Sigma converters have a special low latency filter that is specifically designed to reject both 50 and 60 Hz. This type of filter has a similar response to a sinc filter, but includes an extra notch at both 50 and 60 Hz. Thus, a product using this filter does not need to be customized to work in a specific region. This kind of operation is not found in SAR converters, as they do not contain digital filters and are not usually optimized for DC operation. Aliasing is an effect by which a sampled high-frequency signal appears as a low-frequency signal, called an alias. This alias is indistinguishable from other low-frequency signals that are not aliases, and we generally want to avoid them. To prevent aliasing, we must consider the Nyquist criteria, which states that the input signal frequency must be kept below 1/2 the sampling frequency. An input signal with a frequency greater than 1/2 the sampling frequency will create aliases. The graph on the left shows aliasing in the time domain. The sampling rate for this example is 1 megasample per second, so the Nyquist frequency is 500 kHz. The input frequency, shown in red, is 900 kHz, which violates the Nyquist criteria, and consequently there will be an alias. The blue signal is the 100 kHz alias. You can see how sampling the input frequency at 1 megasample per second generates the alias in the time domain. The graph on the right shows the same aliasing example in the frequency domain. The red input signal at 900 kHz aliases back to the first Nyquist zone. The frequency of the alias is at the sampling rate minus the input signal frequency, or F alias is equal to Fs minus Fn. Again, remember that any frequency above Fs divided by 2 will cause an alias. This slide explains the anti-aliasing requirements for Delta Sigma converters. Beginning with the top figure, unwanted noise signals can occur at frequencies greater than the output data rate of the Delta Sigma converter. If these signals are left unfiltered, they will alias into the ADC's passband. The passband for a Delta Sigma converter can be as wide as 1/2 the output data rate, as shown in the top right image. A Delta Sigma converter will have digital filters that can help minimize the anti-aliasing requirement. This is shown in the middle figure. The digital filter in gray attenuates the green noise signals in the filter's stopband. However, it is important to realize that the digital filter will also alias or reflect at multiples of the modulator frequency labeled Fmod. If the unwanted noise pickup is near the modulator frequency, it will be left unfiltered and reflect into the passband. That is what is happening with the red noise signals. These signals occur near the modulator frequency beyond the stopband, so they are inside the alias digital filter passband and will be reflected into the first Nyquist zone. The way to avoid this problem is to use a simple external RC filter. This filter will have a first-order low-pass response that rolls off gradually and attenuates the high-frequency noise near the modulator frequency to minimize any aliasing issues. Let's look at component selection for this RC filter in the next slide. This slide shows the most common anti-aliasing filter topology used with Delta Sigma converters. Note that the common mode capacitors from each input to ground are 10 times smaller than the differential capacitor. This is a common approach, as mismatch in common mode capacitance due to component tolerance will convert common mode signals to differential signals. Using the smaller common mode capacitor values sets the cutoff frequency higher than the differential filter. This assures that any signals that are translated from common mode to differential will be attenuated by the differential filter. This topic will be covered in more detail in later videos. For now, the main point to understand is that the delta sigma anti-aliasing filter is very simple. Now for comparison, let's look at a typical anti-aliasing filter for a SAR converter. Here we show a typical SAR system with an anti-aliasing filter and the charge bucket filter. The charge bucket filter is used to absorb transient charge kickback from the SAR input sample and hold circuit. In a later video series, we will cover this topic in great detail. But for now, you should understand that this filter is not designed to be an anti-aliasing filter. Generally, the cutoff frequency of this filter will be set to be 10 or 20 times the sampling frequency of the ADC, whereas an anti-aliasing filter needs to have a cutoff less than half the sampling frequency to be effective. In this example, you can see that the charge bucket filter cutoff is set to 16 MHz, even though the sampling frequency is 1 MHz. In this example, the anti-aliasing filter is an active, second-order low-pass filter with a cutoff frequency of 10 kHz. This filter has an attenuation of 60 dB at the Nyquist frequency, so it functions as an effective anti-aliasing filter. An important point to make here is that the SAR typically does not have an integrated digital filter, so an external active filter that has significant attenuation at the Nyquist frequency is required to prevent aliasing. The delta sigma converter, on the other hand, always has an integrated digital filter, so the anti-aliasing requirements are significantly relaxed. One last comment on ADC filtering. Some products will include integrated filters. For example, the delta sigma converter shown on the left includes an RF frequency filter to protect against electromagnetic interference, or EMI. This filter is effective at frequencies in the hundreds of megahertz to gigahertz. It minimizes the effect of RF frequencies on the delta sigma's PGA. Even though the PGA bandwidth is significantly lower than the RF frequencies, noise pickup in this frequency range can cause large shifts in the amplifier's offset. So, the filter effectively minimizes the effect of RF noise pickup. The SAR converter shown to the right incorporates an integrated anti-aliasing filter into the design. This is very helpful, as no external anti-aliasing filter is now required. In fact, this design incorporates an internal PGA, reference, and reference buffer, so that the complete signal chain is contained in one device. This concludes this section on extrinsic noise. Now, let's take a look at intrinsic noise. Intrinsic noise is naturally occurring noise that is generated by the circuit components themselves. This noise typically has a Gaussian distribution, and the noise levels can be predicted through calculations or simulations. Some examples of intrinsic noise are thermal noise, jitter from a clock source, voltage reference noise, and quantization noise. Since the clock jitter noise and other thermal noise sources are all Gaussian, they are indistinguishable from one another and can be combined using the root sum of squares. Here we will first define clock jitter, and in the next slide, we will see how clock jitter translates to noise in an ADC system. Clock jitter is random variations in the timing edges of the clock source. Note that this variation has a Gaussian distribution. Depending on the quality of the clock source, this jitter can be minimized. An expensive precision phase lock loop, or PLL, can limit the jitter to very low levels. Clock jitter errors are mainly limited to AC type errors because the jitter affects the aperture delay in an ADC. This slide shows how jitter in the clock can affect the ADC accuracy. In simple terms, the point in time at which the signal is captured will vary from sample to sample. This produces a voltage variation that looks like white noise superimposed on the input signal, shown here as a sine wave. As a result, clock jitter raises the noise floor in an FFT. Inspecting the formula on this slide shows that higher frequency input signals, or larger clock jitter, increases this error. It makes sense that higher frequency signals are more susceptible to clock jitter, as the slope of the waveform you are capturing is more steep, so the error will be greater for a fixed amount of jitter. Also, A larger jitter time clearly introduces more error as well, since the conversion result has more time to deviate from the actual desired sample point. Finally, the equation at the bottom calculates the best case signal-to-noise ratio, considering only clock jitter as the noise source. Notice that oversampling has the effect of averaging the jitter out. Thus, the best case signal-to-noise ratio due to clock jitter is improved by a factor of 10 times the log of the oversampling ratio. This is only applicable to delta sigma converters. This slide graphs the signal-to-noise ratio as a function of frequency and jitter. As expected, the signal-to-noise ratio gets worse for higher frequency signals and also for larger clock jitter. Also, you can see that the oversampling ratio shifts the signal-to-noise ratio by a factor of 10 times the log of the OSR. For lower input signal frequencies, jitter may not be a significant issue. On the other hand, for high frequency devices, jitter may be the fundamental limiting factor to performance. The high-speed data converter video series covers the topic of jitter in great detail. For now, the goal is to emphasize that the delta sigma converter uses oversampling, so it has some inherent immunity to jitter issues. Typically, most SAR converters do not use oversampling, so the graph on the left is more pertinent to SAR converters. In the previous two videos, we discussed noise shaping and digital filters in detail for delta sigma converters. Noise shaping minimizes the quantization noise near the signals of interest, and the digital filter eliminates much of the high-frequency noise. This method allows for excellent low noise performance on delta sigma converters, but is not a feature used in SAR converters. In the next slide, we will look at the noise performance for a precision DC optimized delta sigma converter. Here we show the noise specifications for the ADS-1252 delta sigma converter. This device uses a low latency filter that is optimized for low frequency or DC inputs. The sampling rates shown in this example are 2.5 samples per second and 10 samples per second. The table lists the noise levels for three different filter types: FIR, Sync 1, and Sync 3. The table also shows the associated 3 dB bandwidth for each filter. The main point here is that the low bandwidth and high order filters minimize the noise, as you would expect. Also, it should be emphasized that the lowest noise option in this example has a total integrated noise of 6 nanovolts RMS. This is incredibly low noise, as converters and amplifiers can have total noise in the microvolts range or higher. Of course, this makes sense when you consider that the bandwidth is only 0.65 Hz. So for this example, the converter is optimized to measure a very low frequency signal with minimal noise error. On this slide, we compare and contrast a SAR converter with a wide bandwidth delta sigma converter. It would not make sense to compare the last example to a SAR, as a SAR would never have its bandwidth limited to just a few hertz. On the other hand, the wide bandwidth delta sigma converter will have more similar specifications and applications to the SAR. First, notice that the noise for the ADS-1675 delta sigma converter scales with data rate. This is because the associated digital filter will also adjust with data rate. For this example, the data rate ranges from 125 kilosamples per second to 4,000 kilosamples per second, and the associated noise ranges from 6 microvolts RMS to 44 microvolts RMS. Notice that the SAR sampling rate can be adjusted from 0 to 1,000 kilosamples per second, but its associated noise is a constant 23 microvolts RMS, regardless of the sampling rate. This is because the SAR does not have an integrated digital filter, and any noise on the input will alias back into the Nyquist band, regardless of the sampling rate. At the bottom of the slide, you can see the same phenomena with signal-to-noise ratio, or SNR. Since noise for the delta sigma converter scales with data rate, so does SNR. Conversely, for the SAR, the SNR is constant and independent of data rate. In general, the ADC noise will be a combination of thermal and quantization noise. The DC input histogram is a good indication of which noise source is dominant in a particular device. A single column in the histogram indicates that the device is dominated by quantization noise, as shown on the left. A Gaussian distribution in the histogram indicates that the device is dominated by thermal noise, as shown on the right. For low-resolution devices, the LSB size is relatively large compared to any thermal noise, so low-resolution devices tend to be dominated by quantization noise. The example shown on the left is a 12-bit SAR converter, but delta sigma converters with resolution less than 16 bits will also be dominated by quantization noise. For intermediate resolution devices, the noise will be a mixture of both thermal and quantization noise. SAR converters will often fall into this category. High-resolution devices tend to be dominated by thermal noise. This is especially true for wideband devices, as the noise is not limited by a filter. This example shows a wide bandwidth delta sigma converter, and you can see that the noise clearly follows a Gaussian distribution, so the device is dominated by thermal noise. Note that a DC-optimized delta sigma, running at a very low sampling rate, may have very low thermal noise, so the histogram would show a combination of thermal and quantization noise, similar to the graph in the middle. Now that we have covered noise, let's move on to a new topic. In this section, we will consider when amplifiers are required to drive the input of ADCs and to buffer the voltage reference input. Here we are just providing a brief overview, and later we have multiple videos covering this topic in great detail. The goal here is to provide some general insight into how drive requirements may differ between SAR and delta sigma converters. First, let's consider the options for connecting signals to an ADC. The figure at the top of the slide illustrates the case where an external amplifier is used to buffer the ADC input. The amplifier is often used for wide bandwidth SAR and delta sigma applications, where it is needed to absorb the charge kickback from the internal switch capacitor sampling circuit. Amplifiers may also be used in cases where the input signal chain needs to attenuate or amplify the sensor output to match it to the ADC input range. Finally, the amplifier can help to increase the input impedance to match high impedance sensors. The next case to consider is where a programmable gain amplifier, or PGA, is integrated into the ADC. In this case, the external amplifier is not needed. The integrated PGA is very common in delta sigma converters, but can also be found in some SAR converters as well. Typically, this kind of internal feature is used for the lower bandwidth applications, while wide bandwidth applications use discrete external amplifiers. The last case is where the data converter does not have an integrated PGA, but the sensor is directly connected to the switch capacitor input. Both SAR and delta sigma converters can use this approach. Typically, this is used for low-frequency applications. In this case, the internal switch capacitor circuit will need to charge up and settle through the source impedance of the sensor. All three methods are valid approaches and will be used according to the system bandwidth and sensor specifications. Let's take a closer look at the first case and compare SAR and delta sigma requirements. Here we compare a wide bandwidth delta sigma converter to a SAR converter. Both cases require an external amplifier to drive the switch capacitor input. Frequently, this external amplifier needs to have a bandwidth substantially wider than the sampling rate for best performance. In the example on the left, the SAR converter uses a fully differential amplifier with a 150 MHz bandwidth, even though the sampling rate is only 1 megasamples per second. This is not unusual, as the switch capacitor input to the SAR has transients that are much faster than the 1 MHz sampling rate. Some wide bandwidth delta sigma converters, on the other hand, may use an internal pre-charge buffer that helps to alleviate some of the charge kickback. This type of configuration may still require an external amplifier, but the bandwidth requirement can be substantially reduced. This isn't always the case, and you need to consult the device datasheet to see what the requirements are. Again, this topic is covered in detail in later videos. The last topic to discuss is the reference buffer requirement. This figure shows the different ways that an external voltage reference can be driven. For higher sampling rates, a wide bandwidth buffer is often required to drive the switch capacitor circuit on the ADC reference input pin. This buffer may be integrated in the reference IC, like the Ref 6050 in the second image. However, most voltage references do not include an integrated wide bandwidth buffer. For reference ICs without an integrated buffer, an external discrete amplifier can be used next to the ADC reference input, as shown in the bottom left. A third option is to use an ADC with an integrated reference buffer, as shown in the bottom center. For lower sampling rates, a typical low bandwidth voltage reference will work without a buffer. This reference input requirement may be important for both SAR and wide bandwidth delta sigmas. Reviewing the applications section in the ADC datasheet will show if a wide bandwidth reference buffer is recommended for that particular device. That concludes the theory part of this video. Thank you for your time. Keep watching to try the quiz and check your understanding of this video's content. Question 1. True or false? SAR converters commonly have digital filters that can be used to reject 60 Hz noise. The answer is false. SAR converters do not contain digital filters. Only delta sigma converters do. Question 2. True or false? A simple first-order RC filter can be used for the delta sigma anti-aliasing filter, but a more complex active filter is typically required for a SAR converter. The answer is true. Again, unlike a SAR converter, a delta sigma converter has an integrated digital filter, which relaxes the anti-aliasing filter requirements. Question 3. True or false? Clock jitter acts as a noise source. The impact of this noise source does not depend on the input signal frequency. The answer is false. The higher the input signal frequency, the larger the noise due to clock jitter will be. Question 4. True or false? Oversampling can be used to reduce clock jitter noise. The answer is true. The oversampling or averaging performed by the digital filter in a delta sigma converter can improve noise performance by a factor of 10 times the log of the oversampling ratio. Question 5. The blank converter typically has lower noise for lower sampling rates. Is it A, a delta sigma, B, a SAR, or C, both delta sigma and SAR have lower noise for lower sampling rates? The answer is A. The noise of a delta sigma converter reduces with sampling rate, while the noise of a SAR converter remains constant due to aliasing. Question 6. An input buffer may be required to A. Scale the input level, B. Match impedances, C. Drive the input sample and hold for accurate settling, D. All of the above, or E. Option A and B are correct. The answer is D. An input buffer can be used to achieve all of the above.